There we go. So my name is Heather McDermott, and I'm excited to be able to talk to you today about one of my favorite technologies. That would be ground source heat pumps, which are good for both you and your pocketbook and for climate. So one of the reasons that I'm so excited about heat pumps is that they can be so much more efficient than all of their competitors out there. So if you think about a furnace, the furnace cannot generate more heat energy than the energy contained within the fuel. So the maximum theoretical efficiency is 100%. But when we're talking about heat pumps, we're not burning fuels, we're using energy to move heat energy. And so we can move more heat energy than the energy that we're using to do that movement. So we can, a ground source heat pump, for example, can achieve 300 to 500% efficiency. That means 1 unit of electrical energy can move 3 to 5 units of heat energy. 300 to 500% efficiency, which is really amazing. The other amazing thing about heat pumps is that they're reversible. So a heat pump can move heat from outside to inside in the winter and from inside to outside in the summertime. Your fridge, your freezer, air conditioners, they all use heat pump technology, though those ones are only working in one direction. Heat pumps use the refrigeration cycle, same as your fridge, freezer, and air conditioner. But the ground source heat pumps have an extra loop that collects or deposits heat from the ground. And that's that loop that you see in black and green on the right here. It's a well-established technology, first invented in the mid-1800s. And just as cars have been getting better and better and better over the last 100 years, so too have heat pumps. Modern heat pumps are way better than those that you might have seen in homes 20, 30 years ago. So when we're talking ground source heat pumps, they have that extra ground loop. And there are a couple of different configurations for that ground loop. The most common is the horizontal loop, and that's because it is generally the most cost-effective one to install. You need a fair bit of space for a horizontal loop. The way you put those in is you dig a trench 3 to 6 feet into the ground, and you lay down your loops filled with an antifreeze solution. But if you don't have a lot of space, you can put in a vertical loop. And that I've been told you can do in as small a space as 5 feet by 5 feet. You get these big drillers and they drill down and you put the loop in right down deep into the ground. There are a few other configurations. I think Jeff is going to talk a little bit more about them. You can take advantage of lakes and put a loop in there, and you can have open loops that take advantage of underground water. Most people like to know what these things look like. So here on the left, that beige box is the inside component of a ground source heat pump. It's connected to the ducts, so this is for a central system. And if you ask me, it doesn't look a hell of a lot different from a gas furnace. Doesn't take up much more space. But one of the really cool things about ground source heat pumps is that you can take some of the extra heat from the ground or from the inside the home and use it to heat water in this tank. So this A.O. Smith tank that you see here is a water tank that's taking some of that extra heat to preheat water for the water heater. So you can save money in water heating as well. And this is called the de-superheater. It's not necessary, but it's often cost effective to add to your system. On the top, we have a picture of a property that's installing a horizontal ground loop. You can see approximately how deep they've had to trench. And you can also see that it takes a fair bit of space. So this is not usually feasible in urban settings. But you can go with a vertical system in an urban setting. And this here is the equipment used to drill those holes. You've probably heard a fair bit about heat pumps in the last year or so. And the reason you're hearing more and more about heat pumps is because they are the technology that is recommended by the Intergovernmental Panel on Climate Change, by the International Energy Association, by the vast majority of climate action plans for buildings, for decarbonizing buildings. And the reasons are because they are the most efficient technology available to do this. And when they run on clean electricity, they can achieve zero emissions. Right now in Ontario, we have a lot of very clean energy, but it's not electricity, but it's not 100%. You can achieve 34 to 45% reduction in emissions with a ground source heat pump. Heat pumps are also the most economical solutions in most cases, including here in Ontario, and they're a proven technology. You can see from the International Energy Association graph here on the left that their heat pump sales are increasing significantly, and it's not just driven by the European Union, where we know there's a lot of energy issues happening right now. 15% growth in the United States, 13% growth globally, and it will continue to grow. The good news is that heat pumps also save you money, and ground source heat pumps in particular will save you the most. So this is from some of the analysis that I did for the Ontario Clean Air Alliance, and I updated it for January 2023 utility rates. You can see the tallest bar is the 20-year overall cost for conventional gas systems. So that's a gas furnace, an air conditioner, and a gas water heater. The middle bar is for an air source heat pump with a heat pump water heater. And the smallest bar is the ground source heat pump with an electric resistance water heater. Everybody knows that ground source heat pumps cost a lot upfront. And that dark green bar shows exactly that. They are the most expensive upfront, but within that 20-year time frame, they're already saving a homeowner money just from heating costs alone. You add on to that the savings from cooling and the savings from water heating, the savings you have if you're able to disconnect from the gas supply, the fixed customer gas charges, and you're saving even more. But you then get even bigger savings when you take into account the fact that after 15 to 20 years, the home with a conventional gas system or air source heat pump is going to have to start replacing all of that equipment, whereas a ground source heat pump home still has another 5 to 10 years of life expectancy for it. And that's just the ground source heat pump equipment itself. The underground loops are expected to last 50 to 100 years. So that is a lifetime investment. These models take into account the Greener Homes Grant, which is now called the Home Energy Efficiency Rebate Plus program. And I'll talk a little bit more of that in a few slides. So that was modeled under one scenario. Ground source heat pumps are the most cost-effective option under a variety of scenarios. So they are saving $24,000 over 20 years relative to conventional gas systems. You can save more if you live in an older or larger home that needs a larger space heating unit. Saving a little bit less if you have a vertical loop, but you've still got savings in your pocket. Still have savings if you are not able to disconnect from the gas line. Greater savings if carbon taxes continue to rise beyond 2030. But if you happen to live in one of the gas expansion communities in Ontario, then heat pumps become an absolute no-brainer, because you are would be paying an extra 23 cents per cubic meter for your gas relative to everybody else. This means that your 20-year savings with a ground source heat pump is coming in close to $35,000. Very significant savings. Ground source heat pumps differ in a few aspects from air source heat pumps. You have a lot more infrastructure that you have to get set up for ground source heat pumps, so they require a lot more advanced planning. But you do get that greater efficiency. They are on average for heating 300 to 500% efficient over the heating season, whereas an air source heat pump is 200 to 300. Still impressive, but not quite as high. They have a longer lifespan, 20 to 25 years instead of 15 to 20. Of course, they have higher upfront costs, but you can get these superheaters with the ground source heat pumps. Air source heat pumps can be installed anywhere. Ground source heat pumps can be installed nearly anywhere. So there are a few communities where they're not permitted, and there are a few types of scenarios where they are not going to work for you. An installer can let you know. From the utilities perspective, ground source heat pumps offer another big advantage, and that is because on cold winter days, air source heat pumps are less efficient because it's harder to get heat out of really cold outside air, whereas ground source heat pumps are more efficient and they use less power. And that means that as we increase the adoption of heat pumps in our society, the more we have ground source heat pumps instead of air source heat pumps, the less electricity infrastructure we're going to have to build out to meet the extra demand. From a larger societal perspective, both air source heat pumps and ground source heat pumps, when they're electrically driven, can achieve significant emissions reductions relative to natural gas. And those emissions reductions are greater with ground source heat pumps simply because they're more energy efficient. There are a few other things that you might want to consider if you are thinking about a ground source heat pump. You want to plan that installation well in advance. As I noted, the infrastructure that you need to invest in is a little bit more complicated. You may require an electrical panel upgrade, moving from 60 or 100 amps to 200 amps service. But while you're thinking about and planning for that installation, it can be worthwhile to get a home energy audit and find out what it would be cost effective to do to improve the building envelope, because you can save money with a smaller heat pump if you can reduce the heating load. One thing that most people don't know about heat pumps is that they will be more efficient if you do not use setbacks. We've all learned to save energy by setting back the temperature at night and when we're away. This isn't the way to go with a heat pump. And that is because gas is able to increase the temperature fairly rapidly when you're moving the temperature back up. The heat pump can bring that temperature back up, but it does so more slowly. And if you want a big temperature change, it's likely to bring in the electric resistance backup heater to help bring up that temperature. And that is less energy efficient. But the really key advantage to this is if you keep your temperature steady throughout the day, your home is going to be a lot more comfortable. This is a lot more comfortable. I was totally unprepared for how much more comfortable. And that's because your walls, your floors, your surfaces, etc., aren't cooling off in the setback time periods. They take a lot longer to warm back up again. And as they're warming up, they're sucking heat from you. So you're going to be much more comfortable if they remain at room temperature. Some people are concerned about refrigerant leaks from heat pumps, and those are indeed a concern because refrigerants have a very high global warming potential. Those really bad refrigerants are being phased out, but in the bigger picture, methane leaks from gas appliances are a bigger contributor to climate change. And as with any major investment, always get multiple quotes from qualified installers. A couple of good places to look for installers are the HRAI website and the Ontario Geothermal Association websites. Both of them have a place where you can find a local installers. There are incentives available for heat pumps. So the Greener Homes Grant is now called the Home Efficiency Rebate Plus program in Ontario, and it's being run by Enbridge and still available to everybody, all homeowners in Ontario. The grants have been increased to up to $6,500 for a heat pump. There are also greener home loans up to $40,000 in zero interest financing for 10 years. And your municipality may also be offering financing for heat pumps and other building envelope improvements. So have a look at that. If you're wanting to learn more about some of that economic analysis and more about ground source heat pumps, I encourage you to go to the Ontario Clean Air Alliance website and look for this report on ground source heat pumps. You'll see all of the analysis that I talked about today, and you'll also be able to access the spreadsheets that I used for modeling, and you can play with the numbers as you wish. So I hope I've got you interested in ground source heat pumps. This slide will be mailed out to you sometime in the next few days. It has some great links for other places you can find information about ground source heat pumps. And I'm going to switch it over to Jeff.
Thanks, Heather. That was, I think, a good rundown, and I see the questions are flowing. So, yeah, Jeff's going to come in now and tell us in a bit more depth, as it were, about the way that this technology works.
Great. Thank you very much. I'm just going to share my screen here. And Heather, I borrowed some of your slides to do my slides, so thank you for that. Good evening, everyone. My name is Jeff Hunter. Just a couple of notes before I jump into this here. Brad, thank you very much for the introduction a moment ago. Just to qualify, I started working in ground source heat pumps back in 2005. So nearly 2 decades, not more than 2 decades. I don't want to overdate my age, number one. And number two, we saw the cover of the report there, and the OCA report did a fantastic job of looking at the comparisons between ground source heat pumps and natural gas systems. So if you're on the gas grid, in the field, we're seeing a lot of really strong opportunities and applications for ground source in more rural areas where you might be on oil or propane, or maybe still using straight electricity like an electric heater. So there are really strong benefits economically and very strong paybacks for geothermal systems when you're a homeowner that's not connected to the gas grid as well. So just a quick note there. And what I do is my day-to-day is working with homeowners and connecting homeowners to contractors throughout Ontario and helping them, helping guide homeowners to figure out which is the best system for them. And that's what I do every day. So let's jump into it here. Here's the second one I took from you, Heather. I think this image actually was from Natural Resources Canada, a document that's been out for quite a while. It's a little bit of a confusing picture. I want to dive into it a little bit deeper, although I'm not going to get too technical with this. I just want to kind of point out, in fact, how simple these systems actually are. So this is an expanded view of what we were just looking at. This is our heat pump. So in the background here, I have a picture of a heat pump installed, and later we'll take a closer look. But if we were to take all the panels off and dig into the guts, this would be the guts of the heat pump. And this is a very simple system. It only has 1, 2, 3, 4, 5, 6 components to a heat pump. And as Heather said, you're very familiar with this heat pump. You walk by it every day in your kitchen. It is a refrigerator, or if you have an air conditioner already, you're seeing it outside. The only difference between this heat pump, a ground source heat pump, and your air conditioner or your refrigerator is 2 components. This one here looks a little strange. We call that the source coax. And this one here certainly looks a little strange too. And they both do some specific things in a heat pump. This reversing valve, all it does is change the direction of flow of refrigerant. It's responsible for heating or cooling. So when your thermostat, or you go to your thermostat and you change it from heat to cool, all that thermostat is doing is sending a little voltage down to this box and shifting this valve one way or another. So it's telling us where we want that refrigerant to go, and that refrigerant is responsible for our heating or our cooling in our home. And then this second component here, which is different from an air conditioner or a refrigerator, is our coax, our source coil. And if I were to cut that coil, I would see a cross section like this. Now, on the inside here, this is where my loop fluid runs through. So that mixture of water and antifreeze runs through here. And then on the outside, that's where my refrigerant is. And this looks like a very rifled profile. And that's on purpose, because we want to encourage heat transfer. So if the loop fluid is running through the center and the refrigerant's on the outside, we want to encourage heat transfer from the fluid into the refrigerant so it can be carried throughout the system for heating. And then if we reverse in cooling, we in fact want to take the heat from the refrigerant and put it out to the loop fluid so it can be taken out to the ground loop field. So that's the key point. It's pretty simple on how it operates. Very reliable system. It has very few components. Ground source heat pumps in particular are extremely reliable and have an extremely long life. And that's because I'll give you this little scenario here. So if this was an air conditioner or an air source heat pump, the difference would be we wouldn't have this coil. We would have two of these coils. If you can see where my mouse is, that's an air coil. That might be on the inside of the house. So that's inside this box. If it was an air conditioner, we'd have two of those. So one of these would live outside. And you can imagine an air conditioner, it's unfortunate, the day that I need my air conditioner the most is the day that it's least efficient because it's really hot outside. And I'm trying to take heat from inside my house and dump it into warm outdoor air. And it just doesn't do it very efficiently. And in fact, when it's trying to do that, it's kind of like driving your car down the road and just hammering the throttle down to the floor. So I'm always driving at, I don't know, 8,000 RPM, right? As compared to the ground source heat pump, because we're using that constant temperature of the earth that comes in through this coil, it's always just humming away at 1,800 RPM. So it really doesn't see the same stresses that outdoor equipment sees. And that's responsible for its reliability and its long-term life. Now, in reports and studies, when you look at tables and charts, we need to be conservative in those estimates. And so typically they'll say 20 to 25 years. Our experience in the Ontario marketplace over the last 20 years, we see systems 25, 30 plus years before replacement. So it has a really long lifespan because of that reliability. Now, there's one thing that's missing from this graphic here that we haven't discussed, and it's where this text is right here. It's called a desuperheater, because most of us know that ground source heat pumps can do heating, they can do cooling, but they can also provide domestic hot water. And on our common systems, desuperheater is what does that for us. So a desuperheater sits right here, looks kind of like this coil, same kind of profile. It's a little smaller, and it ties in right here. This is really hot gas coming off of the compressor. And the desuperheater looks at this hot gas line and it says, you know what? When it's really hot, there's extra heat there. I'm going to turn on my little pump and I'm going to take some of that heat and dump it into my hot water tank. So it's not an on-demand heater that you open your tap like a tankless water heater. It's not like that. Open your tap, it turns on. No, all it does, it turns on when there's extra heat and it dumps it into a storage tank so that you can use it later. The other key thing I want to point out here is that this is not a magic process. We have to power the process. We got to get it going. We got to start it. We have to power it through, and we get that power from the grid. So we have an electrical power input to this compressor. Now I want to talk about what is power for a moment, just to frame the value of ground source heat pumps. And if we were to define what power is, there's two ways that we define that. Number one, it's the rate at which energy is being converted from one form to another. And I'm going to explain that here in a second. But number two, it is also the rate at which energy is being transferred or moved from one place to another. And so we know where we're going with this. We already know that heat pumps move energy, but what is the rate at which energy is being converted? How do we convert energy? Well, our furnace converts chemical energy that's stored in our fossil fuel, in this case, natural gas, which is methane. So there's chemical energy stored in that methane. How do we get it out? Well, we pipe it into this steel box that you put into your basement. We add a whole bunch of air, you light a match and you throw it in. Well, not so much like that, but we do ignite it. We have controlled explosions in this steel box in the basement. And that's how we extract the chemical energy stored in methane and turn it into heat that's usable. Now, unfortunately, there's a couple of byproducts there. It's heat, which we use, but then we have the bad stuff, which is emissions that we dump into the atmosphere. So a furnace also has electrical energy as well. So just like a heat pump, we have to power it as well. In the HVAC industry, heating and cooling contractors, we typically quantify the rate of energy conversion in what we call BTUs, or British thermal units, per hour. And we look at a house and we rate a house's energy loss in British thermal units per hour. So how much energy is this house losing depending on what the outdoor temperature is? If it's cold out, it could be losing X amount of BTUs per hour. So let's say it's losing 60,000 BTUs per hour. I need to replace 60,000 BTUs per hour worth of energy in that house at that temperature to keep it comfortable indoors. Now, you can see we use the denominator in hours, a time rating. It's common for us to measure energy in terms of power that we're using over a given time period. And you're familiar with this, even though if it sounds a little weird, if you pay your electric bill, the power of an electric heater or a toaster that you have in a kitchen, let's say it's 1 kilowatt. So we can convert BTUs to kilowatts or watts. If that 1 kilowatt toaster runs for an hour, we would say it consumes 1 kilowatt hour worth of energy. And that's how you're billed on your electric bill, and that's how you pay your electric bill. So what's another example of energy being converted that we're familiar with already? Solar panels. Solar panels convert direct solar radiation into electrical current through the materials that are in the panel structure. So we're already familiar with this. We see the panels outdoors and we say, well, hey, that's a 7 kilowatt solar PV system. So we're already kind of speaking the language of energy conversion. One more, and this is historical because this is one of the oldest forms of energy. It's a larger scale example of energy conversion at grid scale. Hydroelectric plants, we're taking advantage of the kinetic energy that is in falling water. And what I mean by that, water that's held at a height. So let's say up here, this is point A, this is point B. In between, we have this dam and it has penstocks that feed the falling water into a turbine. Water that's moving, that's falling, has kinetic energy in it. And that energy is transferred to the turbine. As it moves past that turbine, it spins the turbine. And that spinning turbine spins a shaft, which spins a generator, an electrical generator that generates watts of power. In this case, it's probably megawatts or gigawatts. It's a lot of power, but that's energy in conversion. So again, what is power? The other type of power, or the other way to describe power, is energy that's being transferred from one place to another, moving energy. So this is where geothermal comes in. Ground loops are very misunderstood in some cases, and it's probably because you don't know they're there. Once we're done, they're buried and you can't see them like a solar panel or a wind turbine sitting out there, but they're out there. They are mini power plants that are buried in your backyard because they're providing the same thing that a solar panel is, or a wind turbine is, or the hydroelectric generator is. They're providing watts. It's just they're providing thermal watts, watts of thermal energy, heat energy. And that's what we're transferring to and from the ground. And we're using it for heating, cooling, and hot water. So it's very important to understand that the watts that you get from the ground loop are free. That's free renewable thermal energy that's sitting in that ground loop. If we ignore system installation costs for a minute, just looking at the operation of the system, that ground loop is charged up in the summertime with solar energy from the sun and a little bit of heat from your house or from the building. It's stored there, and then you extract that heat again later on in the winter when you need it. the energy is waiting there. It's free. You didn't do anything to generate it. It generated naturally, and it came from the heat that came out of your house. You don't have to pay for that. All you have to pay for is the process to move it. You just have to pay to power the heat pump to move that energy from the loop into the house and vice versa. Now, the relationship between the amount of energy you use to move it compared to what you get is called the efficiency. And we rate the efficiency of all things. And Heather made an example of a furnace and 95, 98% efficient. In heat pumps, we rate efficiency as a coefficient of performance. It is the output over the input. How much do I get out of it versus how much I have to put into it? So that's called the COP of performance. Now, for a ground source heat pump, again, like Heather said, it's commonly between 3.5 to 5. That means 350 to 500%. I put 1 unit of energy in from the grid, I get 3.5 to 5 out for free from the ground loop. It's 350 to 500% efficient. Now, why the range? There's different pieces of equipment. There's different design parameters. And this is what's important with a designer and an installer, is to choose the right components of the system and to size them properly to optimize this efficiency. Now, that storage and on-demand access to that free renewable thermal energy any time of year, any time of day, is part of what makes geothermal systems so dramatically impactful to the overall process of electrifying space and water heating. Whether we're talking about a single home, a high-rise building, a low-rise community, or even at a larger scale, no other system can provide anywhere near this level of free energy that the ground source system will provide over the course of the year. Or in the case of peak, like Heather mentioned, at those worst case scenarios, when it's really cold out or when it's really hot out, that's when it's really crucially important that the systems that we are using electricity with are using it as efficiently as possible. Now, that's impactful not only for the homeowner, but also for the local electric utilities, if anyone's on the call. If we are making this transition to electrified space and water heating, if we look at the difference between, say, air source and ground source heat pumps, depending on a home, you could have a wide range of difference in electrical usage. It could be 6,000 kilowatt hours a year. It could be 8, it could be 10 worth of electricity annually that an air source heat pump will use more than a ground source. Or at peak, it could be 6 to 8 kilowatt hours or 10 at peak. When everything is turned on and the grid needs to supply energy, that's a significant difference. So the question is, what's the value of those extra kilowatt hours that you're gaining back with a ground source heat pump using these mini geothermal power plants? What's that worth to the utility? Some studies suggest it's worth the cost of installing the system itself. So if there's any utilities on the line, it's something really to think about. Now, Heather mentioned earlier that where can we install a ground heat exchanger? She said nearly anywhere. I want to quantify what nearly anywhere means. This is nearly anywhere. So this little drill rig is fitting into a driveway, not very wide, not very long. Now, this isn't Toronto proper. I know you might not have a driveway. You might only have the front lawn, or maybe you have a laneway in the back. This is like a 350 pickup truck, so it can go pretty much anywhere. What we need to look at here, and certainly in areas like Toronto proper, where you have sidewalks, grass, and then the road, community members need to work with the cities and the towns to get access to those areas. There are already utility corridors there. Thermal energy is a utility. It's a utility scale heat grid. And our utilities, our communities need to work together to open up this space to access that. Now, areas around the world have already done this. This is a community outside of Stockholm, Sweden. All of these boxes, this is an urban area, are geothermal systems installed. And I would note the lowest temperature ever recorded in Stockholm was minus 28.2. We get colder here, so we're on the right path. Now, not always do those little rigs work. It depends on the site conditions and what you're doing. And in this case, this is up Eastern Ontario. You can see the granite in the front. It's lots of rock. So that's going to control the type of system that you can install, the type of equipment that you need to install it, certainly in the vertical case. So there's different considerations. Site conditions will vary. Now, here's a look at a rural application. And you can see if we get the area, we're gonna use the area as much as we can. This is the longest trench you would see. It's about 300 feet long. Now, if we didn't have that length, we had the width, we'd probably try and put it out more over the width, but we had it, so we used it. This would be taken back to a nice rough grade. On the left here, this is the heat fusion process. So what they're doing is actually melting the pipe together. If you put that pipe under a microscope and looked at its crystalline structure, it would look uniform. It becomes one piece of pipe. Now, I want to also address the age or the length of the system life. We hear 50 years commonly. That's because the manufacturers have to limit their liability somewhere. They say, after 50 years, I'm done warranting that pipe. So that's where the 50 years come from. Plastic, this is high density polyethylene plastic. Plastic's a problem for us on the planet. We can't get rid of it. It doesn't decompose, degrade. In this situation, that's a good thing. This thing will outlive you. It will outlive your house. These will last a long, long time. The other option, got one more slide after this. The other option here is lake loops. If anyone from cottage country is calling in, these are very popular. The installers do work with the conservation authorities or any permitting authority that's looking over the lakes. There's sometimes permissions and times of the year that you can put these in, but these are really great heat exchange systems because water is the best way to transfer energy. So they work really well and they're very economical systems to install. And then let's take a look here at the installation in your basement. Most houses in Ontario use some kind of forced air system. And so this heat pump has to be retrofitted into that ductwork system. Heat pumps move more air than a common fossil fuel furnace. So part of the considerations when the installer is looking at things is, how do we adapt to the ductwork system? What do we have to do there? You can see a very large return air drop here, larger plenum adapted to existing ductwork. There's our water tank. There may be another tank back there and there's copper piping that connects into the unit. That's connecting into our desuperheater to store some of that energy when we want to store it. Now, there's also hydronic heating systems. Like I said in the last slide, water is the best way to transfer energy, and that's why hydronic heating is so popular. So things like in-floor heating are low temperature heating systems. Older existing homes that use maybe high temperature baseboard rads or cast iron rads, they require more consideration because heat pumps don't like high temperatures. They work best at a low temperature rise. And so when we're looking at systems like that, we need to really understand what's the building load, how well with the envelope of the construction, how much heat does the house lose room by room, and what do we have for heat emitters in that room, and how do we need to adapt that heat emitter to a lower temperature system. So they're more complex in their analysis and how you approach them, but certainly anything is possible. That is my last slide. I think I'm at time, so I'll leave it there. Thank you very much.
Great, Jeff. That was super informative. You know, I now understand so much more about energy. So I'm going to start to just shout out some questions to both Jeff and Heather and to the folks who've been answering your questions in real time. And Heather, I'm going to start with you because a couple of folks have asked, and I know you touched on this in your presentation, but just to reiterate, when you showed your price comparison, the gas prices you used are current as of now, and did you use net present value for those who understand that language?
Absolutely. So in today's presentation, I was using the most recent utility rates. So that's January 1st rates for gas, and electricity rates changed last November. So both of those, the most recent rates were used, and it was modeled for rural Southern Ontario. In the report, the rates I used were the October 1st rates for gas and electricity. We did not use net present value. We kept the utility rates constant, but applied the increasing carbon cost to the natural gas.
Right, and just to reiterate, Heather's actual spreadsheet is on the OCAA site. So if you want to tinker with that and add net present value, you're free to do so. And what about sort of the volatility of gas prices? Heather, we've seen a lot of volatility in gas lately. I mean, how do these systems help with that?
So yes, gas prices have gone up significantly in the last year or two for a variety of reasons, but the incredible efficiency of ground source heat pumps mean that they are more cost effective to operate, even if gas prices were to absolutely go completely tank, because we also have a rising carbon tax that is being applied to our gas rates. So increasing every year until 2030. And in our modeling, we kept it constant at 2030. But there is talk of increasing that carbon tax after 2030 as well.
Indeed, I think it's probably a fairly good bet that you're going to see that carbon price continue to rise. Okay, so this is maybe a question for Jeff. We did have someone who asked, is this a better system for a place like Ottawa, or even someone else said they'd live somewhere where it goes to -40 on occasion, than an air source system?
Yeah, I would certainly say so, because the important difference is the capacity of a ground source heat pump is not driven by air temperature. It's totally independent. So it's more driven by the loop itself. So as it gets to -40 outside, the heat pump really doesn't know. What changes is your house is losing more heat as the temperature difference between where you're trying to keep the house at indoors and what the outdoor temperature is. So the rate of heat loss through the house increases. And so when we have to size that ground source heat pump to meet that load as much as possible. So yes, I would say because it's independent of air temperature, a ground source heat pump is a much better option.
Yeah, okay. And also there was a couple of questions about whether the loops could be somehow combined or capture heat from a septic system. And someone else was drilling a well and wanted to know if there would be any way to piggyback on that.
So yeah, I'll look at that two ways. So residentially with septic systems, there's offsets. You want to stay away from it because that loop is actually going to get pretty cold, right? If I didn't mention in the presentation, but ground temperatures we're dealing with are really only like 8 to 10 degrees Celsius. And so if we're going to grab some of that heat into the loop has got to be colder than that. So we want to keep it away from freezing any kind of utilities or pipes like that. Although I'll make a note, in urban district systems, there is massive growth in sewage water waste heat recovery. So on a commercial scale, grid scale, larger scale, that is definitely something that's going on. And the other question was open loop. Sorry, I missed
the person was drilling a well, I guess a water well, I would assume.
Yeah, so that is very common in Ontario. From the past, I would say most systems that are installed today are closed loop systems with the piping network, but historically there was a lot that was installed. The two main things to consider there is quality of water, because you're running it through a heat exchanger, which is a metal heat exchanger. So the water has to have the right quality, quantity of water, not only to meet the needs of the heat pump, but also the domestic needs for the house. And the heat pump would use a fair amount. It could be 2 or 2.5 gallons a minute per ton. And then returning that water back to the aquifer. It's got to get back to where you took it from. And it is getting more and more difficult these days, rightfully so, to get permissions to take water, right? So it's a little more challenging.
Right. Now, you showed us a picture of, the difference between drilling through rock and maybe a different sort of soil. So what is sort of the different considerations when it comes to soil type? And is it, if I'm drilling in sand, is it cheaper than, I assume, than going through rock?
Well, yeah, cost is going to, so the different equipment's probably going to drive that cost. So you saw the difference in the smaller rig, which was just drilling into overburden. Then when you get into rock, you're getting more into air hammers and larger equipment. Everything's larger. And so price is going to increase in those situations for sure. For sure, it's a more difficult process. The considerations, though, rock is a great for heat transfer. That's one thing. So it's excellent for the loop as far as transferring energy because it's got a lot of mass to it. With respect to overburden and drilling and overburden in soil conditions, it's definitely something the designer needs to look at and consider because there's kind of two spectrums or two sides of the spectrum. Dry sand, like beach sand, you can imagine it's granular and then there's air gaps in between, no good for heat transfer. Wet sand or fully saturated, or if the water table is high and there's any kind of water in it, awesome for heat transfer, right? So that will impact the design of that ground loop. So the designer needs to, and the installer needs to pay attention to that.
And is that equally true when we're looking at a horizontal loop?
Yeah, you still need to consider that because you could have a horizontal loop. You dig down 6 feet and you're into dry sand. So it is certainly a consideration. Every type of loop, you do need to know what your soil type is or your rock type is.
And how is that determined?
There's really good, Ontario does a good job with their water well records. Like every water well is pretty much listed online and you can get a bit of an understanding of the stratigraphy of the makeup of the ground from where they drilled the well. And then there's installers around the province that are installing geo. They know their areas pretty well. So they know what soils where. And if you don't know, and if it's in the rural area, farmers also know a lot about their soil. So there's many places to figure that out.
All right. Someone was wondering whether, and I think you showed the water-based system, and whether that would be an economic choice, I guess, for a 3-season cottage where you don't have a winter heating load.
When we're talking about economics, it's what is your use case? What is the goal? Some people don't want to have the propane truck coming up the road. They don't want to have to deal with having a fuel supplier like that. So if they have electricity there and they have a lake there, that might be an option for them. And they want a higher efficiency. So it's tough to give you a straight answer on that because it's based on what everyone's use case is. A ground source heat pump system operates between 350 and 500% efficient. It's basically making energy. It's an energy making machine. That's going to cost more than a boiler that only operates at 98%, right? You put 100 in, you only get 98 out. It's a higher cost system as we've shown. So you got to make those decisions relative to your particular use case.
And what are we talking about when we are talking about drilling? What sort of depths are we going to be going to?
That's going to vary too, depending on what you're drilling in. As you can imagine, if you're bringing that big equipment out, you may be more apt to drill deeper with larger equipment. You may be able to drill deeper with larger equipment and you can't with smaller equipment. So smaller equipment may only drill between 150 and 200 feet per hole. Larger equipment, you may go up to 500 feet. For example, in urban Toronto, there's a lot of condos, like high-rise condos that are going geo-exchange these days, and they drill holes that are really deep, 800 feet plus, to get them under the foundation. So it's really based on what's going on in that area, what the design of the system is.
Right. Heather, I had a question about your GHG reduction estimate and whether that's just based on the heating load or that's sort of a heating and cooling scenario, or yeah, I guess that was the question.
So the results for the emissions were for the heating, cooling, and water heating load. And Some people might find that the 35 to 45% emissions reductions is not as high as they might have expected. And that is because we're using marginal emissions factors. That means we are assuming that if you are switching from a gas heating system to an electric heat pump heating system, that the extra electricity used to power that heat pump is not coming from the base load electricity, which in Ontario is coming mostly from nuclear and hydro. It's more likely to be coming from gas powered generation. So it has a higher emissions factor. If we were to use an average emissions factor, the average emissions reductions would be significantly higher.
Right. Thanks for that. I'm just wondering, going back to the soil type question, is there sort of an ideal soil or an ideal set of circumstances where geothermal is absolutely the best? Is that something that's easy to tell without sort of visiting the site?
So I guess the definite what's absolutely the best. So we can already say from a space conditioning water heating standpoint, I can confidently say it's the best heating system on the planet. As far as what you can put into your house, how you heat your house, how it provides the lowest cost of heating, cooling, and hot water, and the comfort level, it's kind of widely accepted that a ground source heat pump is the best. The downfall is you've got to install this network of piping, right? When you put a gas furnace in, you don't go and pay for your own gas piping, right? The gas company does that. So that's sort of the downfall. From the best scenario, as far as everything else goes, there is the best economic scenario. So those rural applications where your only choice is oil or propane or electricity, this is sort of that geo is that key that is really attractive in those situations when you have some land, because the economics are really favorable, if that answers the question.
Yeah, that's great. I just wonder, is the technology growing in popularity? Are we seeing growing interest in it more, or is it remain a bit of an obscure, underappreciated technology?
Is this for me as well?
Anybody who wants to take it, like if Victor wants to comment on this, or.
Well, I'd like to remind people that globally, heat pump sales increased by 13% in 2020 to 2021. And heat pump sales in general are just expected to continue to rise. The ground source heat pumps have always been sort of a minority of heat pumps installed in Canada. And they probably will remain a minority unless there's some changes in policy and incentives. But I would still expect there, as heat pumps become a increasingly adopted, some fraction of those will always be ground source heat pumps because they have so many amazing advantages. Is that upfront investment in the cost and all the hassles associated with installing that ground source heat pump remains a bit of an obstacle for many people. And unless there's some government or other policy thing that can help homeowners to address that, it's likely to remain a small portion. Any other insights?
I just want to add that so what's happening with that in the larger scale is utilitization of the ground loops, and we're seeing that already in the GTA and high-rise applications. So as utilities start to understand the benefit here, just like the comment with the gas grid, thermal energy it can be utilized, and that upfront cost is taken away from the owner of the system. Go ahead, Victor.
So sorry, I'm going to stop. Sorry, I just want to intervene here because I want people to understand what Jeff means by utilitization. So you're saying that essentially the utility is going to install my loop and sell the heat to me as a service. Is that what you're getting at?
That exists today. They're called, energy as a service companies that design, install, operate, maintain these systems. That's what they do. And so for condos, it's already common in the GTA where they put these systems together and then they operate them as a utility to that condo port.
Yeah, I was just going to, just in terms of the popularity of the systems, it was interesting this last Saturday on the front page of the National Post home section, there was a story about geothermal systems in new condo buildings. And so that's certainly, as Jeff was saying, becoming a very popular way to go. Geothermal can be leveraged in new condos without really changing the way the heat is distributed in the suites. It's really just about how the energy is brought to the building, and geothermal is really good for that. And in new construction of new condos, doing vertical loops in the city is really not an issue at all, and that's where they're having a lot of success. In terms of single family homes outside of city cores, we've always done a lot of geothermal in those areas where the cost of heating on propane or oil or electricity, resistance electricity, was always high. So geothermal always had an economic advantage in those communities and continues to have. And now with things like the Greener Homes Grant and the availability of the $40,000 10-year interest-free amortization from CMHC to do those loans, the economics work very well for geothermal in those applications. It's hard to make the dollars and cents work in a retrofit in Toronto, right? If you're living in the city, if you're in a dense, existing mature neighborhood, there isn't a lot of room, so the drilling can get a little bit complicated. And going to a heat pump is still possible, but you really have to weigh the advantages and challenges of going geothermal versus going with an air source heat pump. I think we find in many of those kinds of urban settings right now, the additional efficiency that you get from the geothermal system is it's hard to pencil against the lower upfront cost of the air source system. That's not to say it can't be done, and it's not to say that it can't work. I think Heather's example is a case where she was able to make that work in her house. So it really, I hate to say it again, but it really depends. There isn't like a really clear-cut answer. Each house is going to be unique, and contractors, if you're interested in going through that process, contractors are very happy to help you with that.
Thanks, Victor. There's a question about what sort of the minimum property size you would need for a horizontal loop. What's sort of the, for an average size house, how much space are you going to need? Anybody want to take that? Oh, here's Victor.
I don't. Maybe Jim wants to comment.
I'll chime in.
Oh, there you go, Jim.
So it's hard to give the answer on what an average is, but based on ton of capacity required once you do a proper heat loss, heat gain analysis on your home. Typically on a horizontal loop application, we would want a size to err on the side of caution. Whatever the equipment sizing required to look after that heating load, maybe an extra ton of capacity, because doing a horizontal loop is the most economical way to do infrastructure on a property. So say as an example, worst case scenario for a residential application, with most people, you need a 5-ton system with a 6-ton loop, and 6 tons of loop, you need 6 rolls of 3/4-inch HDPE pipe. Each 2 rolls of pipe would be in a 5-foot deep by 5-foot wide by 300-foot long trench or equivalent. So you need an area, say 25 feet wide by 300 feet long by 5 foot deep, which really, for most people, you have to start looking at a property that's close to an acre or above.
Thanks, Jim. The next question, maybe you could answer this too, Jim, is how close can when you're vertically drilling, how far apart do the boreholes have to be?
Typically, you want to maintain at least 10 foot to 15 foot of diversity horizontally, if you're looking on a plan view from Google Earth, distance apart. But with some of the drilling technology available, like Geosource as an example, can drill on an angle. So in some cases, they can be 5 feet diversity at the surface, and by the time they angle the drilling application, can maintain a really good diversity. By the time they hit, 150 to, in some cases, they're going 850 foot depths on site. So it depends on the driller that's involved with the project. But if you have a driller that's only capable of drilling, 100% vertically, then you want to try and maintain, I would say, at least 10 to 15 feet horizontal diversity.
The boreholes can be a little closer together. The shallower the borehole is, we like to maintain, I think, if we go to a full 850, it's closer to 17 to 20 feet. But like a minimum of like 13 to 15 feet for holes around 500 to 600 feet is usually what we do for rule of thumb.
Darynne, stay with me here because I want to ask you a question about, people are sort of curious as to, it seems like people should be able to share these loops somehow, that we could collectivize this. We could have a neighborhood loop or a block loop or something like that. Have you looked at those? I know you work with a lot of building owners, and curious as to your thoughts on that.
I would say technically anything is possible. With the right drilling technology. I think one of the biggest hurdles we're going to see in the neighborhood or community geothermal systems is the regulatory sort of municipal space. And a lot of times, if you're connecting a number of homes together, you're often having to leverage a right-of-way or like a roadway that is municipally owned. And depending on the municipality you're in, there is sometimes a little bit of work that would need to happen to make that, I think, go smoothly. But we're seeing quite a few, we work a lot with like high density, like condo buildings and things. So we're seeing a number of like towers, like condo towers being serviced by the same large loop, but typically they are on the same property, as that's kind of the path of least resistance. But it's definitely technically possible. It's just a matter of finding ways to connect everyone together.
Yeah,
I can chime in just for a second.
Mm-hmm.
So one thing I'll add to that, it seems to be a big buzzword that we want to have these community or district energy kind of models.
Yeah.
And the fact remains that if you have a district energy model in a community that's all residential development or all wanting heating at the same time, your ability to really capture any kind of efficiencies, if everybody has a house that needs a 3-ton system and they all want to heat at the same time, then you're going to need 3 times however many homes you have in terms of capacity, both in heat pumps and in loop. The district energy only works as efficiently as it can when you have diversity of load. So if you had an IT center where you had to have cooling year round next to a car wash, or a home where you need heating at the same time, there's no big exponential benefits to having a district energy system.
Yeah.
I bat my head against the wall since 2003 with this concept. And I can tell you from learned experience that it seems to be politically in vogue right now to have this discussion, but unless you have diversity of load, the economic efficiency and benefits are just not there.
Yeah. And I think like the biggest cost savings of having, a quote unquote like community or district system is getting all of the drilling done at once. And I think that can be done if all of your neighbors, for example, all kind of sign up and say, we will hire a driller, and that driller can be here for a week and do all of the drilling all at once. And we don't necessarily have to be connected. Because I think to Jim's point, if you don't have the diversity, it's almost a waste of money to try to connect everyone. There's a lot of lateral piping that has to go in, and that costs quite a bit of money. So I think if you can leverage the economies of scale by having everyone installed at the same time, I think that would probably serve you a lot better.
Great. I'm going to ask one more question, and then I think we're going to wrap up for tonight. The issue of combining a geothermal system with a sort of a more conventional cast iron radiator system has come up with, and I know Jeff touched on it, but people are also asking, is there sort of a hybrid option that can give you the temperature boost you need to use older rad type systems?
Is this for me?
I'll try and chime in. Oh, go ahead.
Okay. No, go ahead. Go ahead. Sorry.
The short answer is geothermal or air source, like air to water units or geothermal water to water units to do hydronic systems do not work effectively if the distribution system you have requires a temperature of greater than about 110 to 115 degrees Fahrenheit. I work in Fahrenheit just because I'm older, but most, like if you look at the worst case scenario, which is those little water rads that look like electric baseboard heaters, they need about 160 to 180 degrees Fahrenheit to effectively emit heat into the space of any meaningful amount. Cast iron rads are typically in that at least 135 to 150 Fahrenheit range. So a geothermal or an air source heat pump under themselves, unless you're willing to either supplement them and continue to use a gas boiler, or to switch the rads to a higher efficiency rad that can emit heat with a supply temperature in that 110 to 115 range, you're presented with some real challenges to be able to keep up with the heating load of your home.
I'd just like to add that the answer to many of these questions, if the question is it possible? The answer is often yes. It doesn't mean that it's a good idea. And it doesn't mean that it's the norm and that contractors are going to feel comfortable with it. So, this question's come up in the chat a couple of times, and if to Jim's point exactly, if what you have is a high temperature emitter, especially if it's baseboard emitters, right? So if you've got a copper fin tube kind of emitter that needs a very high water temperature, then geothermal is not the right solution, right? And can you add a gas boiler to get the temperature up? You can, but the economic payback of this system is going to just get longer and longer and longer. And so you need to really consider, why are you trying to do it? What's the purpose? And just to carry on Jim's second point, the best thing to do in that case is to change the style of emitter. And so you see this a lot going on in Europe right now, in Germany and in the United Kingdom, where there's been a big move to heat pumps because of the cost of natural gas. Those homes typically had hydronic heating systems, so they're going from gas boilers to air to water heat pumps. So they're not going geothermal as much, but air to water heat pumps. Same challenge, the output water temperature is in that 110 degree range. And so what it means is changing out what we call them heat emitters. They're radiators, basically. Heat emitters, we're going with more surface area, right? So the radiators, they look nice now. They're often, stainless steel, painted stainless steel type things. And they're panels, they're heat panels, they can be painted, but they get bigger. And that's kind of the way we solve this problem of how do we get the heat into the space at a lower temperature? We need a bigger surface area. So that's generally the better solution than trying to use a gas boiler for injection.
Great. Okay, I have one final question for Darynne, just because I'm curious about this too. So how do you get the loops to hook up at the bottom of the well?
So they're actually, the loops that we use are fused U-loops. So they actually come with a U-loop bend fused to them from the factory. They're pressure tested in factory and everything. So we actually don't connect the loops at the bottom of the hole like perhaps it was done in the past. The new technology they have these days is pretty astounding. So it's one single piece of pipe that goes down and comes up all by itself. And all we do, not all we do, but we insert it to the bottom of the hole and make sure it's grouted and it's properly sealed. And Bob's your uncle.
Fantastic. So, you know, this technology is, just as with air source, obviously steadily improving with these new drilling techniques and the like, really interesting. So I would just like to thank everyone for, especially our panelists and our helpful experts for joining us today. And we will be posting the answers to the questions in a few days once we get those sort of cleaned up and collectivize some of the answers. Those will be, we'll send out those and a link to the recording. Probably you'll be looking at receiving that next week. Please, when you get that information, feel free to share it widely with your neighbors and friends and tell them about this great technology and everything you've learned tonight. And so finally, you know, thanks for joining us and supporting our efforts to move Ontario to a 100% renewable future. And if you like what we're doing, of course, you can make a donation through the website at cleanairalliance.org. So once more, thanks for joining us and good night.